Assalamualaikum and hi, I'm binti Azrul Nizam. So today, I will start our mini project presentation with abstract. Leukodye-based thermochromic inks are specialized dynamic inks that change color when exposed to a different temperature. They are colored when exposed to a temperature lower than their activation temperature. At 4 degrees Celsius below the activation temperature, the color begins to fade. It is widely used in biomedical and pharmaceutical industries, as well as the textile and novelty industries. The purpose of this study is to determine the efficiency and dependability of thermochromic leukodye based on coated non-woven mask in detecting temperatures changes by changing the color at a specific temperature set point, with the potential to serve as a tool for early detection of fever. Next, the study of the development thermochromic face mask using a thermochromism concept and the benefits of the development for future use in the medical industry and the user are also part of the objective of this study. A non-woven face mask thermochromic slurry and binder were used to develop the sample of the thermochromic face mask. The method including pigment, paste and curing process was devised to test the effectiveness and functionality of a thermochromic face mask coated with blue thermochromic ink with an activation temperature of 42 degrees Celsius. The blue thermochromic color-coated non-woven face mask begins to fade at 38 degrees Celsius, which our thermometer readings to indicate a fever. 4 degrees Celsius below the activation temperature and eventually becomes colorless at 42 degrees Celsius, revealing the face mask white tint. We conclude that the development of thermochromic face mask for future use in the medical industry and the user can assist the medical practitioners in recognizing the patient's condition earlier. Despite the busy and unstructured environment at the hospital, and the use of thermochromic face mask will make people more alert with their surroundings in their daily life.
Move on to the introduction part of this mini project presentation. The world is now dealing with a little virus disease caused by the severe acute respiratory syndrome coronavirus disease 2019, which is known as COVID-19. Meanwhile, Dr. Nur Hisham Abdullah, the Director General of Health, has firmly declared that wearing a face mask in crowded place areas is mandatory. Therefore, as all of us are aware, wearing face masks in public has been made mandatory from 1 August 2020. On top of that, we come up with the idea of designing a smart non-woven face mask that would change color by utilizing the thermochromic concept to alert us if our body temperature is too high. As we already know, the major function of the mask is to block any big particle droplets and splashes that may carry germs, which is virus and bacteria, preventing them from entering the mouth and nasal passages. However, we have improved the features and usefulness of the face mask to the point where it can provide indications through color changes of the mask when our body is in a high temperature state. This face mask is recommended for usage in a hospital. It will assist medical practitioners in recognizing the patient's condition early despite the busy, unstructured environment at the hospital, particularly during this current outbreak. For instance, those who intend to visit a hospital or clinic must put on this mask before entering the building. This act also can alert others if the user is suffering from a health problem that includes a high body temperature. Instead, they might be prioritized by clinicians in terms of treatment and care. In addition, it also can benefit the society and environment to take extra precautions when they meet the user of thermochromic mask in public by only seeing the changes color, and people will aware with the health condition of the user. Thermochromic materials first appeared in the laboratory in the early 1950s. This led us to the concept of thermochromism, which refers to a change in color caused by temperature fluctuations. Thermochromic leukodyes are leukodye-based thermochromic inks that are specialized in dynamic inks and can change color when exposed to temperatures below their activation temperature. They are commonly colored at room temperature, and above their activation temperature, they are transparent or faintly tinted. In other words, while the leukodye is cold, it is colored, but as it warms, it becomes transparent or translucent. The activation temperature is calculated as the solvent transitions from a solid to a liquid condition. The ink has nearly achieved its light color endpoint, forcing the color-forming components to come into contact below the transition temperature, which is the colored state, and separate above this temperature, which is the discolored state. Furthermore, leukodye is commonly combined with other pigments, which non-heat sensitive pigment, to change the hue from one to another. They come in a variety of colors, temperatures, and forms, including powder, slurry, water, and solvent-based ink, epoxy, and master batch. The use of leukodyes has the advantage of being more resilient and less costly than liquid crystals, since the unique technology of applying the thermochromism concept using the thermochromic leukodye is more simple and easier to handle. It has been used in the industry in making certain things such as product labeling, packaging, graphic, and toys, and many more. In fact, the application of the thermochromic leukodye is wider. For instance, leukodye has been used in product labeling and packaging in bottle wrappers. The leukodye's term will start functioning by turning the mountain at the bottle wrapper become blue. This means that the water is cold. Besides, when the mountain at the bottle wrapper turns grey, it means that the water is at the usual temperature, which is not so cold. If this technology has been used widely in the future, it will make people easier to know the temperature of the water in the bottle when wanted to buy drinks without touching those bottles. Other than that, to attain certification in manufacturing the novelty product, the leukodye powder was blended with the binder, and this technology popularity has grown. As we can see at the gift store, there are a variety of heat-sensitive marks with unusual yet appealing designs to the customers. Apart from all of these applications, the development of thermochromic face masks can also be manufactured using the thermochromic leukodyes, as face masks are becoming a part of our life now with the ongoing COVID-19 crisis. Next, the thermochromic leukodye is composed of a color developer and a color former. They are mixed in a solvent and combined to produce a thermochromic composite. The composite stays solid in a non-heated state, and the color former takes on its colorful structure. When in a heated state, the solvent melts, and the interaction between the solvent and the color former destroys the composite, causing the color former to take on a colorless form. The temperature at which the solvent converts from a solid to a liquid is described as the activation temperature. To adhere, it is combined with a binder to adhere the thermochromic leukodye ink to the fabrics are substances that may build a three-dimensional layer on the surface of a textile substrate to hold pigment particles in place.
Next, we move to the methodology. For the pigment paste, the thermochromic pigment powder was mixed with the fabric binder in a ratio of 1:1 and was diluted with a small amount of distilled water. Next, the mixture was kept mixing to prevent the separation of the thermochromic pigment powder and fabric binder. Then, the mixing of the mixture was continued using a high-speed stirrer for 5 minutes to ensure a homogeneous paste. Next, for the applying on face mask section, the white non-woven face mask was placed on an aluminium foil, and the pigment paste was applied to the non-woven face mask using a paintbrush and was allowed to completely dry. Last but not least, for the curing process, The painted non-woven mask was cured using the hairdryer to set a maximum activation temperature for 3 to 5 minutes.
Based on the slide, we can see that there are 3 boys under the 3 different conditions, which are 24 degrees Celsius for the first boy, for the second boy is 38 degrees Celsius, and the third boy is 42 degrees Celsius. So, at the ambient temperature, which is 24 degrees Celsius, the thermochromic face mask does not change the blue thermochromic color, while at the 38 degrees Celsius, which is at 4 degrees Celsius below the activation temperature, the blue thermochromic colors starting showing the reactions and disappear. Meanwhile, at the activation temperature, which is 42 degrees Celsius, the blue thermochromic color become colorless by showing the true color of the face mask. In this case, it clearly shows that the thermochromic color become colorless and reverse the actual color of the face mask that we used in the previous methodology session. For the next part, we did 3 testing tests on the thermochromic face mask, which are particulate filtration efficiency, bacterial filtration efficiency, and differential pressure test. All these 3 testing tests are following the American Society of Testing and Materials, which is known as ASTM F2111 standard specification. ASTM is the international standard organization that develops and publishes voluntary consensus technical standards in healthcare. Move on to the first testing test, the particulate filtration efficiency, also known as PFE. This test measures the percentage of particles larger than 1 micron filtered out by the face mask. So, how we succeed this test? This is actually by aerosol of 0.1 millimicrometer polystyrene latex particles is sprayed on the thermochromic face mask at flow velocities of 0.5 until 25 cm per second. The next testing test is a bacterial filtration efficiency, that also known as BFE. This BFE test is to quantify the thermochromic face mask material's performance in filtering out bacteria larger than 3 microns. We know that previously I have mentioned that BFE test filtering out bacteria larger than 1 micron, while for BFE test it's filtering out bacteria larger than 3 microns. To achieve this test, an aerolized liquid suspension of Staphylococcus aureus, which means particle size of 3 plus minus 0.3 micrometer, is shooting to the thermochromic face mask sample at a constant flow rate 1 ft3 per minute. And for the last testing test is a differential pressure test, which also known as DP. This test determines how breathable a mask by measuring how easily air passes through from one side to another side. To achieve this result, a controlled flow air is driven through the mask and the pressure before and after is measured. This difference in pressure is divided by surface of the sample, like a lower breathing resistance indicates a better comfort level for the user.
Now, we move to the discussion part. According to the Merriam-Webster Dictionary, the thermochromism is the phenomenon of the reversible color change of a metal with a change in temperature. In this context, heat is used in the technique to modify the equilibrium space between the aligned crystal packing of the molecules. These changes occur as a light wavelengths are substantially diffracted, causing the color of the substance to be seen. Besides that, the thermochromism concept was applied in only certain things which are thermochromic materials such as leucodies and liquid crystals. In addition, thermochromic leucodies and leucodide-based thermochromic inks that may change color when exposed to temperature below their activation temperature. The activation temperature is obtained as the solvent changes from a solid to a liquid state. At room temperature, they are usually colored. they are clear or lightly colored above their activation temperature. Based on our studies in this project, the blue thermochromic pigment that coated non-woven face mask begins to fade around 38 degrees Celsius, which is oral thermometer readings to indicate a fever, and eventually goes colorless at 40 degrees Celsius, revealing the white color of the face mask. This phenomenon can develop as a result of the thermochromic concept. The structure of the leukodye-based thermochromic ink is composed of color developer and color former dissolved in a solvent and mixed with thermochromic to form a composite. The composite remains solid in the non-heated phase, and the color former maintains its color structure. When heated, the solvent melts, and the interaction between the solvent and the color former destroys the composite, leading the color former to revert to its colorless condition. Other than that, binder is another core part in the development of a thermochromic face mask. It is a material that is used to dilute the leukodye-based thermochromic ink, effectively thinning it down so that it spreads smoothly on cloth without thickening or becoming brittle, while still providing good adhesion characteristics. Furthermore, the efficiency of the thermochromic leukodye-based face mask can be evaluated by observations and comparison of testing test results and experimental results. The efficiency of the blue thermochromic ink slurry was demonstrated by a temperature change of roughly 4 degrees Celsius below the activation point, which is 42 degrees Celsius. As a result, it is effective and dependable as a tool for early identification of fever. Aside from that, we decided that PFE result was 73% and the BFA result was 84% based on the findings of testing on the thermochromic face mask. According to the ASTM F210011 standard specification, both of these results are classified as level 1, which is sufficient to prevent the transfer of respiratory droplets caused by coughing or sneezing. There are a plethora of applications on thermochromic face masks for future use, as these thermochromic face masks can be used at clinics, hospitals, and medical centers. This is because it can help the doctors and nurses at the premises to alert with their patients by looking at their patient's face mask. For instance, medical practitioners will become easier in notifying most needed patients to be prioritized to get the treatment first, because the thermochromic face mask will give a sign through the color changes when someone's body temperature is high. In addition, the mask will change the color using a thermochromism concept, and people who are having health issues such as fever can wear the thermochromic face mask to make sure that people surrounding them can keep some distance between them. And if this type of face masks are being used by all people in the public, it will make the community to always alert with their surroundings all the time. Last but not least, the conclusion ends. Based on this mini project, we discover how the thermochromism concept may be applied to the non-woven face mask as a tool for the early diagnosis of fever. Aside from that, we determined the efficacy of the thermochromic face mask based on the test result, which included particle filtration efficiency (PPE), bacterial filtration efficiency (BFE), and the differential pressure (DP). It has demonstrated how attentively we endeavor to produce a thermochromic face mask that meets the ASTM requirement. By changing color at a predetermined activation temperature, we examine the thermochromic leukodye's efficiency and reliability in sensing temperature changes within the face mask. This thermochromic face mask has a high potential for use as an early detection tool for fever. A study of the development of a thermochromic face mask by using thermochromism concept had been achieved successfully, as by the end of this project we are clear about the materials and the concept of thermochromism, which it will change in color if there are any differences in temperature.